In this final section of multiple integration, we're going to take a look at the idea of what a Jacobian is. A Jacobian is essentially going to be a U substitution for multivariable integrals, except instead of a U substitution, it's going to be a UV, or in fact a UVW if you want to translate into 3 variables. So essentially what you're doing is you're taking one variable and you're transposing it into 2 variables. You may recall that in Calc 2, when we took a look at the idea of just a single variable, we used the U substitution. We had this definition. We had the idea that if you had an integral f of x dx, we could translate it into an integral of this form, f at g at u times the derivative of gu. Okay, that's our U substitution. We're going to do the same thing in Calc 3, except now we're going to be doing that by utilizing a multivariate function. And you might think, why would you ever use that? So let's say for some reason we have these regions and they're very difficult to make either a type 1 or a type 2 region. So we have this example to where we just have maybe like a sine-like function going both horizontally and vertically. And we get these non-rectangular regions. The idea is to utilize this transformation. So we define t to be a transformation, and then all we're going to do is we're just going to utilize that transformation to make all of those non-rectangular regions into a rectangular region. Okay, so the whole idea is to be able to take non-rectangular regions and make them into rectangular regions. To be able to do that, we're going to take a double integral and we're going to use a change of variable. And the change of variable that we're going to try is we're going to let our single variable x equal to some function in terms of u and v, and we're going to let our single variable y equal a different function in terms of u and v. So in other words, there's a relationship between x and y that can be expressed as functions u and v. The Jacobian is essentially going to be the absolute value of the determinant. So we're just going to take the determinant, we're going to find the partials with respect to x and y and u and v, and we're just going to make a determinant out of that. And all we do is we just multiply partial x partial u with partial y partial v. We subtract from that partial y partial u, partial x partial v. You may recall when we were taking a look at the different types of coordinate systems. Specifically, we took a look at the cylindrical system and we took a look at the spherical system. And you may recall that we had these multipliers. You may recall we had r, dz, dr, d theta. And that was a multiplier that we had that took rectangular and turned it into cylindrical. You may also recall that we had rho square sine phi d rho, d phi, d theta. So we had another multiplier. Those are essentially both Jacobians. We just never coined them using those terms. And those are the multipliers that we took using multivariate functions and translated them into other multivariate systems, and there was a multiplier that ensued. As a basic example of that, we know that the change of variables from rectangular to polar coordinates, we know that x is r cos theta, and we know that y is r sine theta. And we've gotten this r dr d theta when we translated from rectangular to polar. And the question is, where did that come from? And we proved that geometrically. We can also prove that using these Jacobians. So first what we're going to do is we're going to start by finding the partial of x with respect to r. We're going to find the partial of x with respect to theta. We're going to find the partial of y with respect to r. And then we're going to find the partial of y with respect to theta. All of those are extremely easy. Partial of x with respect to r, cos theta, derivative of r is 1. The partial of x with respect to theta is negative r sine theta. Partial of y with respect to r, sine theta. And then the partial of y with respect to theta is going to be r cos theta. We are going to take these four partials, and we're going to plug them into this determinant, except instead of u and v, we're going to use r and theta as our variables to plug in. Okay, so to be able to find the Jacobian, we're just going to make a determinant. And remember, we had cos of theta, and we had negative r sine of theta. We had sine of theta, and then we had r cos of theta. And recall, to be able to evaluate a 2 by 2 determinant, all you do is you multiply down, you multiply up, and then subtract. So we're going to wind up with cos times r cos. So I'll just write it out the first time. So r cos theta minus a negative r sine theta sine theta. Clearly, this just becomes r cos square theta plus r sine square theta. We can factor out an r. We get cos square theta plus sine square theta, and then we're just left with r. So the Jacobian is just that r. And then, of course, we have the different multipliers dr d theta. So this is another way that we can illustrate that multiplier to go from rectangular coordinates into polar coordinates. So that's just a very elementary example of a Jacobian. Now, in the next series of examples, what we're going to do is we're going to take a non-rectangular region, we're going to change it into rectangular, and then we're going to be able to evaluate some double integrals utilizing these Jacobians.